Hi, Calc 3. How's it going? It's going good? I hope so. Today we're going to talk about Lagrange multipliers. And this is our last lesson for our multivariable functions unit where we use derivatives to optimize stuff and partial derivatives and all kinds of stuff. So, last lesson in this unit, and we're going to talk about one more way to do optimization, because why not have another way? So, the method of Lagrange multipliers is really a way to do absolute max and absolute min. Now, we've done that before where we tested inside of a region and then we tested the edge and the corners of a region, and we used those values to figure out my highest and my lowest z value. Lagrange multipliers can be used for the same thing, but often they are used for when the edge of your region is continuous and smooth and doesn't have corners. For example, if you look at this lovely picture here, what if I were to trace like a circle or an ellipse as my region and project it onto a surface? You can notice that there really aren't corners to test. And since my region has a base that's not a function or an edge that's not a function, I can't do that cool thing where we like input the edge function into the multivariable function and made it a function of one variable. I've said the word function a lot. Lagrange multipliers are for when you have often a smooth, continuous border that you want to test. Okay, I've talked a lot about them, but haven't really told you what they are. So Lagrange's theorem says let f and g have continuous first partial derivatives such that f has an extremum at point x sub 0, y sub 0 on the smooth constraint curve g of xy equals c. If the gradient of g does not equal the zero vector, then there's a real number lambda. Okay, that thing right there is lambda. Look, I'm going to draw a little lamb. I guess it's probably a sheep and not really a lamb, but there you go. There's a real number lambda such that the gradient of f at x sub 0, y sub 0 equals lambda times the gradient of g at x sub 0, y sub 0. What? Well, here's what it says. If you remember what gradients are those things where you make a vector out of partial derivatives. So this is really saying f sub x comma f sub y equals lambda times g sub x g sub y. Still, what? Well, that really means that f sub x is equal to lambda times g sub x. And f sub y is equal to lambda times g sub y. So what we get down here is what's called the method of Lagrange multipliers, where you create a system of equations. That system consists of the thing I just said, f sub x equals lambda times g sub x, f sub y equals lambda times g sub y, but those two equations aren't enough to solve because I would technically have two equations and three unknowns because I'd have x, I'd have y, and I've had lambda. If I'm going to solve a system, I need as many equations as I have variables to make it ultimately solvable. So we're also going to remember that g of xy equals c is going to be our constraint curve. That's the edge of our border for our region. Okay. Now, this doesn't make a whole heck of a lot of sense until you do it. So that's what I'm going to do. But you just need to remember that Lagrange multipliers uses this method with a set of three equations. So let's go. Find the maximum value of x squared plus y squared equals z, subject to the constraint that. Okay, first thing I want you to do is to be able to visualize this. So if I, as carefully as possible, try to sketch this, all right, x squared plus y squared equals z is going to be a paraboloid, all right, and it's going to look something like this. And my constraint is x squared over 9 plus y squared over 16 equals 1. That's an ellipse with a minor radius and major radius, for lack of a better term, of 3 and 4. So if I were to sketch this G curve down here, it looks kind of like that. God, that was terrible. Let me try that again. So this would come over here, that would go over there, and this would go back there. Now, I want you to pretend that that ellipse right there is a rubber band, and I'm lifting the rubber band up and then bending it. Well, yeah, letting it touch the paraboloid and kind of letting it bend naturally on the paraboloid. So what's really going to happen to it is when it projects up and onto the paraboloid, it's going to look something like that on the paraboloid. So I'm probably going to have some minimum and maximum values as it kind of bends its way up this paraboloid. Okay. I'm sure I didn't draw that very well, but maybe that rubber band idea is a little bit helpful. Ooh, you know what? Maybe I should show you a rubber band on a paraboloid. I can do that. Look at this. There's one thing this mask is good for. Stupid masks. 2020, you suck. All right. So if I were to take this rubber band as like an ellipse underneath, and I were to put it right underneath, it's going to bend upward like that. And you can see I have a maximum there and a minimum where it touches a little bit closer to the bottom. That worked out pretty well. Thank you, mask. That's the one time I've thanked my mask. I mean, I know it also hopefully keeps me alive, so I should probably thank it for that, but I digress. Let's actually do Lagrange multipliers. Mrs. Vibber, shut up. Get back to work. All right, so what am I supposed to do here? What is F? What is G? So F is your multivariable function. This is technically f of xy equals x squared plus y squared. This thing right here is g of xy equals c. That's my constraint equation. So the Lagrange multiplier says take f sub x and set it equal to lambda times g sub x. F sub y equals lambda times g sub y, and then g of xy equals c comes last. So f sub x is 2x equals lambda times g sub x. Well, g sub x is going to be 2/9 x. And then f sub y is 2y. And then this is going to be lambda times 1/8 y. And then g of xy equals c is just the constraint equation as a whole. So now I'm supposed to be able to solve this thing for x and y and potentially lambda. All right, well, if I want to do that, there's a couple of different things that we can do here. If I want to solve this, I'm going to set this thing equal to 0 and make it 2x minus lambda times 2/9 x equals 0. And that's actually solvable right now because I could factor out an x and get 2 minus 2/9 lambda equals 0. And so that would be x equals 0 and lambda equals 9. Well, that's pretty neat because you know what? If x equals 0, I can immediately plug that thing in here and say if x equals 0, then y squared over 16 equals 1, which means y equals plus or minus 4. So already I have some test points. So just like when we had the absolute extrema test points before, I have them again. And so now I have 0, 4 as a test point and 0, -4 as a test point, which makes sense because those were the points that I could kind of see and imagine on my paraboloid to begin with. Okay, that was helpful. Now, what if I use this other equation and I say 2y minus lambda times 1/8 y equals 0? Then I could factor out a y and get 2 minus 1/8 lambda equals 0. So I get y equals 0 and lambda equals, what would that be? That would be 16. Yeah, that would work. And so if y equals 0, and I plug that back into my constraint, I'd have x squared over 9 equals 1, which means x equals plus or minus 3. So 3, 0, and negative 3, 0. And if you're thinking, Mrs. Vibber, you didn't use your lambdas. I know I didn't. I didn't need them right now because I was able to solve for x and y without them. So just ignore the lambdas for the moment. They will have their time, all right? But I didn't need them right now because all I really needed to do was find possible locations for absolute min and max to happen. I found them, and now I want to test those points in my function, f of xy equals x squared plus y squared. And so let's see, this is going to be 16, 16, 9, and 9. So I know my absolute max value is 16. And I know that that absolute minimum value is 9. It happens twice, but all I care about really is the absolute maximum value and absolute minimum value. Now, if I go back, it says find the absolute maximum value where x is greater than or equal to 0 and y is greater than or equal to 0. So technically, I would ignore these. I'd still get the same absolute max and min, though. So I'm okay. All right. Let's do another one with purpose where we can actually talk about what lambda does. The Cobb-Douglas production function for a software manufacturer is given by f of xy equals 100x to the 0.75y to the 0.25, where x is the units of labor at $150 a unit, and y is the units of capital at $250 a unit. The total cost of labor and capital is limited to 50 grand. Find the maximum production level for this manufacturer. Okay, little bit obtuse. What does it mean about units of labor and capital? Cobb-Douglas is often a way for us to measure the productivity of a company by boiling it down to where can the company put in money? Can it put in money into humans, or could it put money into like automation? So when we talk about inputting capital, that often means capital that goes into some more automation services, whether you want to think about that as robots or instead of people inputting things, putting money into like a software package that would input it for you, stuff like that. So I want to find the maximum production level. Well, the total loss to labor and capital is 50 grand. And I have labor at $150 a unit and capital at $250 a unit, and I need to stick to $50,000. This would be g of xy equals c. That's my constraint. And my f of xy is 100x to the 0.75, y to the 0.25. Okay, let's do Lagrange now. So I need to take f sub x, which is going to be 75x to the negative 0.25, y to the 0.25, equals lambda times g sub x. Well, g sub x is the derivative of the left-hand side of that equation, and that's just going to be 150. Okay, and then I have f sub y, which is going to be 25x to the 0.75, y to the negative 0.75, equals lambda times g sub y, which is 250. And then I have g of xy equals c. Okay. Well, what can I do this time? Got a couple different options here. And what I kind of want to aim for right now, I think, is substitution. I'm going to look at this equation and say, you know what? In this equation, I really have, let's see, I have 75 y to the 0.25 over x to the 0.25 equals 150 lambda. And I have 25 y, nope, that's supposed to be on the bottom, x to the 0.75, y to the 0.75 equals 250 lambda. And so what I could do with this, I think, is I could solve each of these for lambda and then set them equal to each other. So if I solve this for lambda, I'd be dividing both sides by 150. So that would be y to the 0.25 over 2x to the 0.25 equals lambda. And if I solve this for lambda, I would have x to the 0.75 over 10y to the 0.75 equals lambda. And then if I took those equations that are both set equal to lambda and set them equal to each other, I'd have x to the 0.75 over 10y to the 0.75 equals y to the 0.25 over 2x to the 0.25. And then if I did some cross multiplying here, really, multiply so I don't have fractions anymore, I would have 2x equals 10y. And that's pretty good looking, if I would say so myself, because I can solve for x or for y. I'm going to solve for x, though, because I think it looks nicer. So x equals 5y. And now I can bring that over to here and say 150 times 5y plus 250y equals 50,000. So that's 750 plus 250. That's 1,000y equals 50,000. And if I divide by 1,000, I get y equals 50. And if x equals 5 times y, then x would be 5 times 50, which is 250. I don't even have test points this time. I only have one value. So x equals 50, y equals, 250. And it says find the maximum production level. Okay, so what's my maximum production level? It's going to be f of 250 comma 50, which is going to be 100 times 250 to the 0.75, 50 to the 0.25. And if I pull my calculator out, I'm not even going to bring it up. You guys don't need to see this. 250 to the 0.75. Sorry if my microphone's hitting my scarf here. Move it up so that's not too loud. 250 to the 0.75 and 50 to the 0.25. I get 16,718.5. Okay, that's my maximum production level. All right. What does the value of lambda give you? Well, I didn't solve for lambda, so let's see. In this case, lambda is going to be 250 to the 0.75 over 10 times 50 to the 0.75. And that's going to be what? 250 to the 0.75 divided by 10 times 50 to the 0.75. 0.3343. What the heck is that? Well, since this is a video and I can't really have you discover it for yourself, unfortunately, I just have to say it out loud. That lambda is how much production would increase when C increases by 1. In other words, if I changed this 50,000 to $50,001, my production level would increase by 0.3343, which is a pretty powerful thing to know. So it's like, wait a second, what if I didn't invest 50 grand? What if I invested 60 grand? So if I invested 10,000 more dollars, I would increase this by 10,000 times 0.3343. That tells you how much production increases for every one value of increase in your constraint equation. Pretty cool. All right, so this video has gone on for quite a bit here. So what I'm going to do is set you up for example 3, then I'm going to do it myself, and then we'll meet back here. All right, so it says find the extreme value subject to this constraint. Well, if you notice, this constraint has a less than or equal to. So what this means that you have to do is you have to test the edge using Lagrange, and then you have to test the middle using our relative extrema routine, where you find f sub x and f sub y and set them both equal to 0. So what I'm going to do is pause this video and then meet you back here in a moment. Do I know how to pause the video? I do. And I'm back. And I did a lot of work. So let me kind of walk you through this. And if you need to, just pause to copy my work down if you got stuck. But I started with f of xy and g of xy equals c. And I did Lagrange first. So here's f sub x equals lambda times g sub x. There's f sub y equals lambda times g sub y, and there's g of xy equals c. So what I did first is I said, okay, if 4y equals lambda times 2y, that one's easiest to solve. So the first thing I did is I set that equal to 0, and I factored to get y equals 0 and lambda equals 2. Well, once I knew y equals 0, I could plug it into the constraint to find x. So I got this first set of test points. And then when I knew lambda equaled 2, I said, well, if lambda equals 2, I can plug that in up here to get an x value. So I plugged lambda equals 2 up there to get an x value. Got x equals negative 1. Because if lambda equals 2, I have 2x minus 2 equals 4x. So if x equals negative 1, I shoved that back down here. And if x equals negative 1, then y equals plus or minus 3. And I got those two test points. So that's everything I got out of Lagrange multipliers. Those were the edges. And then instead of the edges, I need to look at the interior. So I set f sub x and f sub y both equal to 0. Got x equals 1, y equals 0. So that's my last test point. And then I plugged them all into the function and got an absolute minimum value of 2 and an absolute maximum value of 24 that occurs twice. This was a long video for Lagrange multipliers. So, I'm tired too. So let's take a break and then you can do some practice later on. Have a good one, everybody.